Hello, everyone. Welcome to another episode of Robo Papers. Super glad to have Paul Zhou sharing with us today his paper AutoEval, Autonomous Evaluation of Generalist Robot Manipulation Policies in the Real World. Thank you so much for coming here, Paul.
Yep, thanks for having me, Michael and Chris. Glad to be
Yeah.
here.
Glad to have you. So maybe you can share a little bit about yourself, what's your journey and getting into this space?
Yeah, sure. Yeah, happy to share. So currently, I am a PhD student at Berkeley, advised by Professor Sergey Levin, and I work in the intersection between robot learning and reinforcement learning. And I'm interested in a wide array of topics in robot learning, especially in how do we better fine-tune robot foundation models. So I'm interested in things like how can we take a robot foundation model, how do we make it generalized to a lot of unseen scenes during pre-training, how do we quickly specialize to one particular skill, going from success rate to 50% to 100% with reinforcement learning? And how do we make robots run autonomously for a long time that give us like interesting capabilities such as the AutoEval projects, which is how do we make robots run 24/7 and make evals a lot easier for everybody. Yeah, before this, I did my undergrad at Brown University, where I worked with Michael Littman and George Konidaris on a lot of reinforcement learning topics, and I gradually got interested in robotics, which is why now I am working on robot learning, which is I think a very exciting field.
Awesome. And me and Chris have been talking about just how much evaluation is such a big bottleneck. Like most people seem to think about data or like maybe compute, but at least for me, I think actually I've learned that actually maybe real world eval is the real bottleneck. You can't speed up time in the real world, and the robots break all the time.
Yeah.
Maybe as a start, if you can just share screen, and do you think you can do the demo like now?
Yeah,
We can start
sure.
with the demo first, and just you can just talk through that way.
Sure. Yeah,
Cool.
let me share screen right now, and while I'm doing that, let me just like give you guys a little bit of a motivation of why we're doing this. Even though I'm sure you guys probably have a good idea, but the reason why we started this project is that as you guys know, robot eval in the real world is such a pain. It takes a long time. It requires you to have a physical robot set up in your lab, in your house, and then especially when you're evaluating a generalist policy, when you need to evaluate a single robot policy in a lot of skills. And for each of these skills, you need to do like repeated like 10 to 20 tries at minimum, where you have like different initial positions to try to like single skill. And each rollout takes a long time, especially if you're having like a large policy that inference takes a long time. So when you evaluate a generalist policy, usually you end up sitting by the robot in the lab like the whole afternoon, and then you walk out with back pains and everything. And it just makes development so much slower. So the idea is we really wanted to provide a resource and a method for the community to make iteration of evaluating policies easier and evaluating them faster. So the idea is we would host robots at different locations and make them evaluate autonomously, automating the parts that require human intervention, which is usually detecting whether the policy succeeded and resetting the scene after each episode. So if we can automate these parts and make robots run autonomously, we can have robots just evaluate themselves, basically. And yeah, and that saves a lot of human time because you don't have to be there, and it enables things like you can evaluate policies remotely, so that if you don't have a robot set up in your lab but you want to do robot learning, you want to train robot foundation models, now you have the resources to evaluate on a real robot pretty easily. Yeah, so I can show you guys what our design interface looks like right now. So can you guys see the screen? Yeah, cool. Okay, so right now, if you go to auto-eval.github.io, you can go to this eval live stream and queue link. So basically at the top, what you're seeing is the robot live feed of two of our robots that we're hosting in our lab at Berkeley. And so these are two Widow X robots. They are small manipulator arms mounted on the table, and they can do all kinds of parallel gripper, jaw gripper manipulation tasks. And As you can see right now, these are streamed in real time of what the camera observation images look like from these two robots. You can see the one on the right here is evaluating some policies. The one on the left is currently idle, but as you evaluate your policies, everyone can come onto the site and they can look at how the robot is doing and what the and whether it's succeeding or whether it's not, and monitor the status of the robot if you want. How you can submit a policy is actually very simple. We have a form right here where you can just submit policy as a server. So the idea here is that we would be fully distributing the eval infrastructure, where the users who want to evaluate their policies, they will host their policy as a server, and the server accepts image queries and language instruction queries from the AutoEval server, and the AutoEval sends the policy server images, and the policy server sends back actions, and these actions are actually commanded and executed on the real robot. So we can try, because the drawer robot is idle, we can I can show you guys how easy it is to submit one single policy. So here, for example, let's submit a policy right here. You can put whatever job description you want, and you can select which robot you want to evaluate. You can select the drawer robot, and currently we provide 2 tasks, open or close the drawer. So easy peasy, and then you have to submit where your policy server is hosted. So I have pre-launched a policy server, so now we can just directly input the policy address and port. I'm hosting this on an amazing open source project called board.hub, where you can host your I use it to expose my local policies to the open web. And after you fill out these 5 fields, you can also additionally try to figure out how many episodes you want to evaluate. For example, instead of just evaluating 10 episodes because it takes a long time, you can now evaluate 50 episodes to reduce your uncertainty of the policy performance. And everything is as easy as submitting a job. And after clicking submit, you'll see that your policy is submitted. You will get your eval ID. And if you scroll down to your job listing right here, you will see that your jobs are all listed right here. The jobs that are evaluating right now will show you that it's in an evaluating status, and jobs that are completed will be shown as a completed status. This makes robot eval just as easy as submitting a software job, for example, to a compute cluster, where you can submit jobs easily through the command line, and you can monitor your job status. You can monitor when it finishes, and you can see how many other people are evaluating jobs. Right now, we have a lot of jobs submitted already, and you can monitor the status of your robot with the robot live stream. And you can see that the policy I submitted just now is executing on the robot, and you can have fun watching the robots moving real time. And say after an eval finishes, if you scroll down to your jobs column right here, let's take one of the older jobs, for example. We provide a evaluation report after the evaluation finishes, hosted publicly on weights and biases. So what you can get here is that you can come back and look at the success rates, look at the videos. You can select the episode number. You can look at how the policy is doing for each one and every one of their episodes. You can look at a lot of the other statistics that we log of the success rates, of how long the policy rollout eval is, and even some minor statistics like what is the maximum joint effort of the robot, and then whether some checks failed or passed. And one of my personal favorites is these initial and final frame visualizations, where you can come and look at the initial and final frame of each and every one of the episodes, along with whether the success classifier classified this to be a success or failure episode. So you can actually come in and spend additional human time if you want to figure out, do I trust these results from AutoEval? Because you can easily make sure that they are accurately classifying it. For example, here the policy is to trying to open a drawer, and you can see that the drawers that policies that are opening a drawer are getting classified as success, and episodes where it's not opening a drawer is getting classified as failed. Yeah, so with this system, we are trying to make everyone's lives a lot easier just so that you don't have to sit by the robot and you can submit a job, wait for the report, and in the meantime, go off and do whatever you would like.
It's really nice. Cool. It's a very cool work. That's it seems like a ton of work to put all this infrastructure together, to be honest.
Yeah, thank you. Yeah, we did a lot of engineering work just to get the robot to run autonomously for a long time, to make sure the robot doesn't damage the scene, to have the proper safety system, even to engineer just this UI that are publicly facing everyone. Yeah, and so the this setup runs mostly autonomously, but if you look at a message right now, you'll see that when the robot encounters some dangerous scenarios or encounters a situation where the reset policy failed, you will see that on the website it will say display this message saying awaiting human intervention. And so basically when this happens, the robot will send me a message on Slack telling me you need to come and check on the status of the robot, make sure all the robot joints are okay, all the reset policy is doing okay. And then I can just, if everything's okay, I can press a button for it to continue. So and we did a experiment in the paper where we ran AutoEval for an entire day. And usually this only happens a handful of times where you need human intervention. And the rest of the times, the robot will just go on smoothly.
Cool. So I did want to ask about the reset policy, because I feel like that to me seems like the trickiest part to get something like this to work. Like, how do you handle that?
Yeah, so to make the system fully generalizable, to make it be able to reset any task, our method is to learn a reset policy. So to do this, we collect a small amount of demos, around 50 demos, and fine-tune a robot foundation policy to do the resetting task. And in the paper, we used OpenVLA. So basically, we collected a small amount of demos and then fitted a large foundation model to it. And basically, the model is easily able to do these kind of tasks.
Yeah, this is great, Paul. I've got so many questions. Could you, let's say, comment a little bit about any false positive or false negative? Because it seems to me these are tasks with kind of binary outcome.
Mm-hmm.
The final judgment classifier, I suppose. What's your observation so far?
Yeah. So we also did an analysis of this, and I can actually show you a little plot right now in the paper of what are the failure modes and the limitations of our current AutoEval system. So basically, if you look at figure 11 right here, if we look at a total of 50 runs and where the AutoEval system detects whether it succeeded or failed, most of the failure right now comes from the fact that the reset policy failed. So we actually found that the classifier is pretty easy to train compared to the reset policy. There are some points where the reset policy would fail, and you can try to mitigate this by collecting a little bit more diverse demos, a little like more number of demos. So instead of 50, you can try to increase that number, or you can maybe someone will come up with like better fine-tuning techniques that better leverages foundation models. Yeah, but for a short summary to your question, I think the most amount of improvement that could go into this is to figure out how to train better reset policies and maybe train like reset policies for like much longer horizon tasks, more dexterous tasks, for example.
Yeah, I mean, I guess it is a little bit simpler because it's only one task that the reset policy needs to handle, but getting the perfect reset policy is basically the same problem as you're trying to solve, right? Like you're trying to learn it. Well, you're
Yeah,
trying to
yeah.
get remote
So
learning to work, so it's going to always be the challenging part, I would imagine. Yeah.
yeah, exactly. Yeah, so the nice thing about this is that because the reset policy only needs to handle one task, basically it's okay if the reset policy is overfitted to these demos. And actually we want it to overfit to a small amount of demos. So we don't encounter a lot of the classical challenges of like during pre-training, for example, of how do you train on like a lot of different tasks. We just need to be able to fit a big model onto a set of demos.
Yeah, it makes sense.
So it seems that there's no force failure. Can you imagine some scenarios where there could be force failure? Or
You
you
mean
just
for the success detector? Yeah, so
yeah.
definitely. So you can definitely imagine a scenario where the policy actually failed, but the classifier thinks it's a success. For example, if you started out, that depends on like if you started out never training on any images where there are occlusions happening in the scene, the classifier like it, for example, in our drawer task right here, if you think about where the robot has never seen like the entire robot arm like just basically occluding the drawer, basically you will never be able to figure out like is the drawer open, is the drawer closed, because all you see is the robot hand. So in development, we had a iterative style where we train a classifier, we deploy it to see what kind of failures we could encounter, and then we would add more training samples to robustify the classifier to try to get rid of these kind of situations. And right now it's pretty robust.
Yeah, so I guess that is force success. I was just wondering whether there's force failure. I mean,
Yeah.
it's it thinks it failed, but it actually succeeded. Because
Yeah,
in that
that would be
flow
like
chart
if
just now, you
the
didn't have that.
yeah, like if the eggplant was not visible or for some reason in the placement area, right? That would be and then the classifier said no. That would be like an example of a false failure. Not sure if that can come up in this case, right? That's what you're thinking, right, Michael? Yeah.
Yeah. So in those cases, we actually train a classifier. So in the drawer case, we train a classifier to detect whether the drawer is open or closed. And in the eggplant case, to handle like these kind of scenarios, we actually train a classifier to output like 3 different classes, whether the eggplant is in the blue sink, in the yellow basket, or anywhere else, basically an invalid position where the eggplant could be out of the scene, could be like in the middle, like in the air, in the gripper of the robot, or it's like falling on the table somewhere else. That helps it makes the classifier a little bit more robust here.
Yeah. Like I could imagine
Got
a
it.
case where like if you had like lots of other objects in the sink where it still ends up hidden, but actually in the correct target. Like if the robot arm knocks something else in on top of the eggplant, right? But maybe you
Yeah.
could do that with a video model or something if you wanted to resolve it. I'm
Yeah.
sure there's a way. Yeah.
Yeah. So if you really want to make this system like really robust, you can also imagine like adding a different camera from a different angle where you can see things from different perspectives, and you train classifiers just not from a single image but from multiple images.
Yeah, makes sense.
How about like things like scene reset? Have you guys explored those? Like for example, maybe the drawer is in a slightly different position. The initial, I guess, state.
Yeah. So maybe an easier example is like the eggplant scene here, where like basically the eggplant could be like anywhere in the blue sink or anywhere in the yellow basket, and we actually observe this is the case for our experiments. So I can actually show you a visualization right here in the appendix of the paper, detailing the initial positions of the eggplant. So basically, if you run a lot of trials for the eggplant, we will see that the eggplant actually is in a lot of different initial positions in the sink. And And to deal with all these different kind of neutral positions, how the reset policy deals with this is basically we just collect demos that are with the eggplant spread out through the sync so that the policy has an idea of how to actually handle these eggplant and handle the depth perception, like for example. And it helps a lot that we are fine-tuning a good robot foundation policy, because this policy has the pre-trained ability to already know how to handle some variability of where the object is. So we're kind of like tapping into that capability and just giving it a little more demos to know how to do it robustly in this scene.
Yeah. How about, I guess, the motor failures and whatnot? I imagine if someone sent a really crappy policy, it immediately break your arm and what?
Yeah. So
How do you guys handle
I'm
that?
glad you asked. So that was that was like a whole effort in trying to design the system, is that we took care to try to prevent these from happening like as best we can. But there are really about 3 layers of safety for our current AutoEval system. So the first safety net is we have a workspace boundary such that we control that the robot arm is not able to go out of the workspace. For example, it's not allowed to come back and hit the camera and like adjust the camera angle, because it's limited to a certain bounding box. So but inside this bounding box, we also try to prevent the robot from colliding into the scene, for example, like smashing into this eggplant. So what we do is that because the WidowX robot doesn't have native impedance control, basically we implemented our own very, very naive impedance control system, such that whenever the robot has a high force contact with the sink, the eggplant, the drawer, the robot doesn't keep pushing into the object, and it will cut off the actions. The final safety failure is that basically at every step, we monitor the health of all the robot joints. And if a robot joint fails, we basically reset the robot to sleep position, reboot the motor, and then restart the eval episode. So we ensure that for each and every one of the episode that AutoEval runs and includes in the report, all the motors will be perfectly healthy for all of the evaluation episodes.
Yeah, sounds like a huge engineering and logistics effort getting all this done.
Yeah. So we spend spend a lot of time designing all these infrastructure, but all of those infrastructures are now open source. So it's for everyone, especially using the WidowX robots. There are a lot of amazing infrastructure to use to keep robots running autonomously, whether for like AutoEval or for like autonomous like online learning of all kinds of stuff.
Nice. And the WidowX is a relatively cheap arm too. This is $2,500 or so, right? So that's really nice for good.
Yeah, so it's a pretty affordable hardware, and then it comes with the bridge dataset, which is about 60,000 trajectories. So people who are interested in robot learning can get an affordable arm and try to learn on a large scale dataset.
Has anyone broken an arm yet? I know you haven't been running it that long, but has anyone managed it? No.
Well, not to the point where it's unsalvageable. We've definitely, especially in the early phases of the project, like hit points where like the gripper is broken, and we need to replace the gripper. But I think that was before we had a proper like impedance safety net. And now it's been running about 2 to 3 months, and the robot hasn't broken down since.
That's pretty impressive, especially with like the really low cost hardware like that. That's great.
Yeah. So I think with a little bit of software efforts, we're making it at least a better platform than before to run robot experiments.
Yeah, so I guess in your paper you compare this setup, or use this setup to compare a bunch of policies, right?
Mm-hmm.
So basically, how maybe some researchers who are comparing between different policies, could you show what is the final output amongst those policies? I guess in a way, how researchers look at the final results when they compare.
Yeah, so basically, we compared against these set of generalist robot policies. We compared against OpenVLA, which is a 7 billion parameter vision language action model. Suzy, which is a hierarchical model that takes in language, generates a Go image with a image editing diffusion model, and then runs a Go conditioned low-level policy for that language conditioning. And then Octo, which is a transformer trained on the cross-embodiment dataset, the Pi0 models, open source implementation, and mini VLA, which is a 1 billion parameter vision language action model. We ran a lot of these policies, and actually one of the very nice things about AutoEval is that if you're trying to compare your policies to, if you're training your generalist policy and you want to compare to other generalist policies, you can basically get this comparison for free. Because one is that you don't need to run these results yourself by sitting in the lab. You can run it autonomously using AutoEval, or you can reference our numbers in the paper. You can reference other people's more recent runs of these policies if you want. And you can and you can rank policies this way. And so basically what we found when evaluating these models is that none of them, like there's no model that achieves like there's no absolute optimal model. Like some policies perform better on some tasks, some policies perform better on other tasks. But in general, OpenVLA and OpenPy0 are pretty decent at these tasks that we look at.
But I guess the more important thing here you're trying to show in this chart is that whether it's human evaluating or AutoEval evaluating, they basically get you the same conclusion.
Yeah. So exactly. So one of the main questions that we explore in this paper is that, like, is AutoEval results trustworthy? Like, can you trust it compared to ground truth human run evals? And for all the policies that we run here, that our evidence is that you can. We have a really strong correlation between AutoEval scores and human eval scores. Actually, we have a Pearson coefficient of 0.99 compared to simpler, which is a evaluation in simulated environments, but more photorealistic than traditional sims, and offline metrics such as measuring validation loss, the MSE loss on a validation set, which actually correlates the other way with human evals. So that shows that, like, if you run your policy on your real robot setup where there is no gap between the settings that you want to evaluate your policies on, and your reset policy and your success classifiers are sufficiently good, then you can get really good performance correlations.
I'm a bit surprised that the simulation is this bad.
Yeah, so
why do you think that would be the case?
I think we found that for simpler evaluations and maybe sim evaluations in general, is that it really depends what policies you're trying to evaluate and what scene you evaluate it on. Like, some policies would correspond pretty well to their real world evaluations, but for other policies it doesn't. I think we've found this like across like multiple institutions, like multiple PhD students have experienced this issue, and it depends on like which task you're trying to evaluate it on. It doesn't always give you the most reliable signal if your end goal is trying to make things work robustly in the real world.
Yeah, I guess this is another chart to a strong case for doing things in the real world and not simulation.
Yeah.
So what do you think is the kind of productivity like increase? Like I can't think of a good metrics, but like offhand, do you think you just run way more evaluation now that you have this?
Oh yeah. Let me actually show you a visualization of how it compares to human running evaluations. So here is a plot. Figure 9 is a plot that shows the evaluation speed of AutoEval compared to human eval. So as you can see, the gray line here indicates the average human evaluation speed, and the blue line here indicates the average auto eval speed throughout 24 hours of the day, and the blue bars indicate like the actual real-time speed. And so overall, the auto eval speed is slightly lower than human eval speed, but still somewhat comparable. But if you count that AutoEval can run 24 hours a day, run 7 days a week, then and humans only work during the day, then it actually saves over 99% of operator time, because for humans using AutoEval, your time is basically only required for human interventions. Basically, you need to whenever I got pinged on Slack to check on the robot, to spend like half a minute to a minute here, and then I need to check everything's okay. I need to click the continue button, and then that will be it.
Yeah, this is 99% better because humans cannot work 24/7. Damn.
Yeah, and if you're using our two open access setups, then you actually don't spend any minute, because I will be the one doing the human
Right.
operator.
Yeah. Yeah. So
Sorry, Chris.
this is a slight change of subject. So if you have something on topic, Michael, maybe.
Well, I do want to ask. So in this case, this is, let's say I'm a researcher based in Singapore wanting to test some of my policy, and let's say I host my server in Singapore. Your setup, I believe the server is probably somewhere in Berkeley, let's say.
Mhm.
So obviously there's some latency and things. In general, has that been a problem? And can you speak to the kind of like frequency, both in terms of actions and also in terms of like the video coming back?
Yeah. So that's a great question, Amanda. I'm glad you asked. So I think in general, if you're talking about like any robots, especially of high frequency control robots, then that's definitely gonna be a problem where there's gonna be inference delays. But for our setup, it hasn't been a problem, because for Widow access, we usually use blocking control. So basically, the robot will wait for your action and execute it fully before returning another observation and asking for another action. And I think even for high, like if you need to have like more high frequency control task, as long as your task is not, it doesn't contain anything that's really time sensitive, such as like tossing a ball into the basket, then you can afford to wait around for a delay and execute your action or your action chunk fully before getting another action chunk for the policy server. But if you're doing like very high frequency and time sensitive things like tossing a ball, pouring water, then you might want to rethink how, like, where the policy is hosted. You might want to host the policy locally where the server is.
This actually was relevant to what I was going to ask then. 'Cause, I was going to ask about why you guys ended up choosing the particular like server port structure in the first place. Because when I was at Meta, we actually did a little bit of like benchmarking and designing a benchmark like this. It's unfortunately not live anymore. There it was like upload a Docker image. The Docker image has internet access, so if you want to connect to a server, you do it from there. Now that's a lot more work to host, but it does get around some of these issues. So do you you have any thoughts on like with this? Yeah, what is the justification idea? I guess
No, I'm glad you brought it up, because the Docker solution is actually that was one of our like proposed solutions compared to this, because that gives you like a lot more control over how things can be, how the server can be done. But the reason that we use this like open internet like server and port thing is just I wanted this resource to be like as easy to set up as possible, such that if you have a policy, you can build your server in like 5 to 10 minutes, and you can submit a policy right away. And since that the two robots we're hosting isn't in the high frequency domain, and we do blocking control, then I figure let's just make life easier for everybody, and let's not deal with all the Docker stuff.
Yeah, that's fair. Like, yeah, dealing with the Docker stuff definitely can be a bit of a that's understandable.
Yeah,
and I imagine there may be some models where at inference it requires tremendous compute. let's say I don't know, and maybe
Yeah,
you as the
exactly.
host, you just don't have that, right?
Yeah, like if anyone sends in like huge model, then I can't guarantee we have compute 24 hosted.
Yeah, or actually it's just some vibe coding and then it's actually just GPT-4o at the back. Just look at it and then okay, this is my guess.
Yeah. Yeah, so this gives the user a lot more flexibility of like where they want to host things, how they want to set things up, as long as they conform to the AutoEval API.
Makes sense.
Yeah, I guess just to stretch that dynamic scene thing a little bit more, just so as a scenario, do you think this setup can be done where let's say you have two of these arms in the same scene and you ask one of them to pick up a eggplant, the other one to pick up an orange. They kind of operate in the same scene, so they may bump into each other, but they don't bump into each other in the way that like it's still pretty slow because both arms are slow. Do you think this will work?
I think it will work as long as it's possible to train a good reset policy. I imagine the classifier is not a harder problem than a single arm, but you may need to have a good robot foundation policy that can like decently operate a bimanual setup, and you may need slightly more demos to fine tune this model.
Got it. Yeah. So I guess we're going into a little bit of the limitations and maybe constraints on this setup. But could you go through? I know you mentioned a couple more in the paper.
Yeah. So yeah, so I can actually just show the limitation sections right here while we talk about it. So yeah. So there are a couple of limitations. So the first one you might think of is that it takes a certain amount of time to create this auto eval setup such that the following policy evaluation becomes essentially for free. But I think a lot of that initial setup cost is done because we built the whole infra for it. So now we have a step-by-step guide of how you can build a whole new auto eval cell to put policies on. It takes roughly about 3 to 5 hours to to collect the demos, train the classifiers, train the reset policies, and build a entirely new auto eval station. But this is an upfront cost you need to pay in order to eval the policies.
About how long did that take for you guys?
For the entire project?
I mean, I guess how long do you think it would take to add a third environment? Let's say that's a better way.
Yeah. So I think if you do it on the Widow X robot where we have everything set up, then it definitely only takes like just 3 to 5 hours is enough. We have very easy infra for demo collection, for success classifier training, for reset policy training, and everything should happen super fast. And then we have all the safety systems set up for the Widow X robots. But if you want to do this on a new robot, especially one that doesn't have these safety nets, then you might need to spend time like migrating the safety nets to the new robot, which will probably take maybe a few days. Yeah, but if you have a lot of evals you want to run on this robot, I would still say it could be worth it to set up a new station. Yeah, especially if you're trying to evaluate generalist task, because one of the visions we have is that hopefully in the future, how we will do evals is that there will be a distributed system of eval stations. There will be these 2 or possibly more hosted at Berkeley. There will be some hosted in other institutions. Be auto eval stations hosted across the globe, and then you can tap into this network of eval stations. And if you have a generalist policy, you can just send your software jobs to like a dozen of these eval stations.
Okay, so that actually brings me to a different question that I wanted to bring up. So like,
Yeah.
so these Widow X arms, they are these low cost robot arms, and we know that there's like often slight differences in like calibration and like mechanical properties between them. So if you have one in Berkeley and you have one in like NUS or something to make it easier for Michael to test his policy, like do you think that they would give meaningfully different results? Or are there cases where they might give meaningfully different results? Like just
And so you're asking like if Michael
Yeah.
wanted to like replicate my exactly same setup that I had set up here in
Yeah.
Berkeley, like would he be able to get the exact same results?
So there are a couple of reasons. Yeah, particularly like how much is this? How variable is performance on the hardware to start with, right?
I think like there's definitely variable like on the hardware, like how like what's the status of your joints, or like how old your robot is. And even for Widow X robots, we figured out that like it matters if your motor is overheating. If you like operate it for too long, the motors overheat and your performance staying consistent. We have to like we have a system that rests the robots every 6 hours during AutoEval. And even things like other than the hardware of setting up the scene, if you're trying to replicate a scene, like even if you have a little bit of distribution shift, if you have a different table height that this matches, if you have like a different camera angle, like things will lead to differences in your policy performance. So I think in general, it's very hard to exactly replicate a robot setup in two different places.
Yeah.
So
Yeah, I mean,
so that's why I think we shouldn't be thinking about replicating like the same thing exactly at different institutions, but you should just evaluate different policies on exactly the same scene and then create different scenes at different institutions. And then everyone has access to all the scenes.
Yeah, I think that's a good point. A nice way of thinking about it. Have you noticed much difference with like the age of the robots? Does that because like it would also be a shame if like I ran Pi Zero fast or so, or Open Pi Zero or whatever it is, and like 6 months later it was I rerun that experiment and then it does worse, right? So like
Yeah.
maybe the objects get nicked up and stuff like that, right? What do you think?
So I think it's a possibility, though we haven't observed that. So we ran a study that was 2 months apart, and the policy performance were
Great.
almost exactly the same after like 2 continuous months of auto eval operations. I can't speak to like longer periods at this time, but I think the safety nets really help such that the robots joints don't get too damaged, and also the objects in the scene don't get too damaged because objects could age during evaluation, but
Yeah.
we haven't observed too much aging during the 2 to 3 months.
yeah, I think that in fact you might actually want to embrace those variability, right? That even though it's the same model, the actuators look different, or it's just different lighting in Singapore versus let's say Berkeley on on a winter cloudy day. Even though it's so-called it's the same scene, same task, same arms. I think what I love about this is that I think there's just there's a dearth of like neutral eval. It's like every lab do their own eval, and you just have to trust whatever the lab claim that they do in their own settings.
Yeah.
Whereas you can now do this kind of like as a service to the whole community. I mean, clearly this one has a lot of limitation because just so much logistics, and every time you change an arm, a different arm model, you got to like it's a big engineering challenge. I think mostly engineering, but I think this give a very good baseline. It's like it's so simple. Like everyone who have new policies just by default send it to auto eval, do the base things first, and so like and this is a baseline that hopefully the community can easily trust, because it's especially when you start to have distributed. I imagine Singapore have one, London have one. Just
Yeah.
different university.
Also harder to
very
game if
similar
someone
setup.
else can stand up a bunch of new ones, right? So you can't like you would notice like if it did really well before this date, and then someone and then like I don't know ICL adds a bunch of arms, and then suddenly your policy does worse. That means you were overfitting, right? Something like that.
Yeah.
Yeah.
So it contributes to like making robotics a little bit more reproducible than what it is now. Like if you have your policy, you claim it to do really well, then people can run your open source code on open source evaluations and see if it really matches up to what you say it is.
Like I mentioned, at the start, I think this is a very much needed. Me and Chris were just chatting about this for a few times now. It's for me, I'm not a researcher, but when I look at this, usually the first thing I look at is success rate. But at the back of my mind, I always thought like, okay, how much should I trust his success rate? Firstly, the denominator usually is very low. When they say success rate is out of 10 tries, I was like, oh my gosh, like this is not even statistically significant. You want at least thousands. Then it starts to make sense. So having something like this just get you to the thousand first of all, and because I think it generally can be trusted a lot more. Like it's, anyone can just verify.
Yeah, exactly. Yeah, it gives you the ability to run a lot more trials than just 10 trials. Like yeah, if you see results that are like just reports higher, better results out of 10 trials, like is it actually better or is it just due to noise? But yeah, with automated evals, you can run for much longer, and then you can trust a little bit of the reproducibility aspect.
Got it. So is there any like future work that you guys are thinking of to further extend this, or like you do more go back to your RL's research? Because this one
Yeah,
is
so I think
yeah.
yeah, I think we're working on both. I'm definitely still thinking about the eval problem. How can we make evals a little bit easier for everyone? What is the right way of doing evals? What are the best practices? For example, like how do you compare policies? How do you do A/B testing against policies? But yeah, I'm also concurrently working on a lot of the learning problems of how do you make fine tuning faster with reinforcement learning with VC stuff like that.
But yeah, I mean this is really cool. Chris, do you have any more questions?
No, I think this is great stuff. I think that benchmarking is like a huge problem in robotics, and it's nice to see someone with a actionable solution for it. So great. Yeah, no questions.
Yeah, we don't have our own MMLU like
exactly. We were just chatting about this, like how
Yeah.
I think this is this is definitely not the whole solution. Hopefully this is a small step towards that solution. I think if we have a lot more available tasks that are hosted distributed, then we can really make this a holistic benchmark for generalist policies.
Yeah. I mean, it does seem like I would, of course, love to see mobile manipulation somehow get tested, but of course, things like that start getting much more and more complicated and harder to build into a framework like this. But I think that there are ways you could do it.
Okay, cool. So maybe as a final question, usually we always end with this. Are there any cool papers that you come across that you think was I mean, need not be related to evaluation, but any cool robotics paper that you think you just want to give a shout out to? Maybe we can also reach out to those authors and ask them to come on the show.
Oh yeah. Do you have any particular sub areas in mind? Robotics is
anything. It could be even like computer vision. Whatever you think, just pick your interest.
Yeah, I think So I personally I'm interested in as I've said like robot learning and reinforcement learning. So I'm really interested in how can you use RL to fine tune robot foundation policies. So I think there is a paper called Policy Agnostic Reinforcement Learning from CMU that's pretty cool of how you can use RL to every kind of like diffusion policies, VLA policies, and I think it's a cool result.
Cool, this is awesome. Yeah, we will definitely take up that paper. Okay, cool. I think that's it. Thank you so much, Paul. It's been a really fun chat for me.
Thank you, and thanks for the live demo. It's the first one that we've got.
Yeah, happy to share you guys. Yeah, this was fun. Yeah, thank you for the invite.
All right, Chris, what have you learned?
All right. So this was I thought this was a cool paper. It's a nice piece of kind of infrastructure, like community service, to be honest, like the kind of thing that I feel like makes robotics as a field easier. So what they did was like what he did was making sure that there was this platform where you can set up your robot and to evaluate policies and make it easier to test out. And I think like we've talked about this before, and I think in the podcast, but like robotics evaluation is really, really hard. Robotics evaluate, like generally, I think robotics benchmarks aren't very trustworthy. And it's nice to like, even though there are some real limitations, obviously, but even given that, like it's really, really nice to have something like this that I think people can build their own setup, and you can test it from anywhere, and they got all this web access. Yeah, what did you think?
Yeah, exactly. I think this is actually the more than the lack of data, maybe the even bigger bottleneck towards robotics. Like, how do you know, and how can other also trust like the performance of what you claim your model, right? And and because you can't speed up time, anything that can automate the real world evaluation process just helps. And the way they've done it is, they've done it in a very let's say cost-effective manner is what I think. And there's a lot of nice goodies that they already built, like some safety features that's already built. Everything is open source, so
A lot of
I'd love
software
to
work
see.
just to make it work well. Yeah,
I mean,
it's
just
like
the engineering is insane, I think.
yeah, I mean, this is another one of these things with like robotics. Like as you know, like I feel like keeping robots working for like 3 months straight is pretty difficult. It's pretty like actually, especially if they have it like running 24/7, connected to the internet. You did say it was taking breaks every 6 hours, so it gets its time off. But like, but still, most of like 3 months of uptime is pretty impressive, right? And especially if you're letting random people on the internet execute policies on your robot. So that's right. Yeah.
Yeah, exactly. Yeah, very curious to see. But I mean, it's still, despite all the work that they have done, and obviously they've open source everything. It's still non-trivial, I imagine, for let's say, and someone else in the community who want to say replicate that. Like, there's just so much other work that is associated, right? I
The
mean,
training the reset policy in particular is the big one, getting that to work well. Because
even
until
the
you get
human
that,
intervention, right? You never know, like, even though it's AutoEval, but it still breaks every now and then for whatever reason, right? As we saw just now, right? The human intervention pop up, right? The window. So, which means you still kind of need humans around a little bit. But it's definitely very much needed, and we need more, actually, this kind of service.
yeah. I mean, if you didn't need the humans around, we probably also wouldn't need the benchmark. Is my probably they'd be good enough, right? Like that's it. Yeah.
Yeah, exactly.
Yeah. But
Yeah. Cool. Well, anyway, it's been a fun chat. Let's do it again soon. Cool.